Hello, my name is Stephen Hawking, physicist, cosmologist, and something of a dreamer. Although I cannot move,
and I have to speak through a computer. In my mind, I am free. Free to tour the universe and tell the ultimate story. The story of everything there ever was. From the moment the cosmos began, to the creation of our world and everything in it, and beyond, to the far, far future and the end of the universe itself. A journey through all of space and all of time.
check it out.
I spend a lot of time thinking about the universe, but I never get bored. After all, it's a pretty extraordinary place. This is the cosmos, at a very large scale. Each tiny point of light is an entire galaxy, each a cluster of as many as 400 billion individual stars. This view of the universe is only possible due to the latest supercomputers. I find it indescribably beautiful. Uncountable billions of galaxies forming a vast web stretching away in all directions. What's more, I never get over the fact that within this massive universe lies one perfectly ordinary spiral galaxy. Inside that galaxy exists a commonplace yellow star, orbited by 8 planets. On one of those planets lives a species that has only just worked out what a remarkable place the universe is. Us. We've discovered more about the cosmos in the last century than in all previous human history. Finally, we are solving the basic mysteries that have perplexed our ancestors for at least 200,000 years. What I like above all is that the facts themselves are both breathtakingly elegant and surprising. We're living just as it dawns on us that the Earth and everything around us was made by the stars. Boiling furnaces of hydrogen gas, like our sun, made even the atoms in your eyelashes. We've worked out that the universe is almost unimaginably ancient, about 14 billion years old, and that it will continue to exist for at least twice that long. But without a doubt, the most remarkable fact of all is that the entire enormous universe, all the innumerable galaxies, even time and space, and the forces of nature themselves, simply materialized out of nothing. So now is a good time to be alive,
I think. We may only be an advanced breed of monkey, living on a small planet, but we are able to contemplate the universe as a whole, which makes us very special. My goal has always been simple, to work out how the universe works, and why it exists at all. Luckily there are clues everywhere, and the most important one is right above our heads.
Examine any patch of the night sky, even one as small as the head of a pin, and this is what you'll find. A tiny part of the vast web of galaxies. It's less than a millionth of what we can see of the cosmos from our little planet. But even this tiny sample is enough to find the clue, the key to the past, the present, and perhaps the future too. The clue is that seen from Earth, all these distant galaxies are slightly red in color. They appear almost as if we were looking through rose-tinted glasses. It's this very redness that reveals how the universe was born. And to show you why, I need a straight road and a noisy car. Listen to the sound as it passes by. As the car approaches, the pitch of its engine rises. As it goes away, the pitch of its engine falls. This phenomenon is called a Doppler shift, and the exact same thing happens with light. If our eyes were more sensitive to color, we could see that the car is actually very slightly blue as it approaches, and very slightly red as it goes away. The same rules apply in space. All distant galaxies are slightly red in color. So by the exact same piece of basic physics, they must all be moving away too. In fact, the whole universe is expanding in all directions, getting bigger and bigger, like a balloon inflating. I admit this sounds strange, but to cosmologists, it's like winning the lottery. Because to work out where the universe came from, all we need to do is to stop time and make it run in reverse. Rewind far enough, and everything gets closer together. A lot closer together. All the galaxies, in fact, every single thing, converges to a single point, the start of everything, 13.7 billion years ago. So it's quite simple, really. Follow the clues, and we can deduce that a very long time ago, the universe simply burst into existence. An event called the Big Bang. But I'm afraid we have to stop a moment before we get carried away by fire and noise. At the very beginning, the Big Bang actually happened in total darkness because light didn't exist yet. To see it, we'd have needed some kind of cosmic night vision. But even this, a view from the outside, is impossible. Again, it sounds strange, but space didn't exist then either. So there was no outside. The only place there was inside. This early universe was a very strange thing indeed. There's still much I'd dearly love to know about it, but standard concepts of time or space don't really apply. It was just a very tiny, ultra-hot fog of energy. Then it expanded with a tremendous flash of radiation. From smaller than an atom to about the size of an orange in less than a trillionth of a second. Almost no time at all. The universe simply inflated into existence, unfolding, unfurling, getting bigger and cooler with every passing moment. Within 100 seconds, it was as big as our solar system, trillions of miles across. While this was happening, the pure energy of the cosmos began to cool and create matter in the form of countless trillions of subatomic particles. The first stuff there ever was. Half these particles were made of matter, the same kind of stuff which makes us. The rest were made of the opposite of matter, stuff called antimatter. When the two meet, they destroy each other in a flash of energy. It seems as if building a universe is a pretty wasteful process. Fortunately, there was just a bit more matter than antimatter. Just 1 in a billion particles of stuff survived. Which was lucky for us, because that residue is what our present-day universe is made of. You could say that we are made of the smoke of the Big Bang. By the time the cosmos was 10 minutes old, it was already thousands of light years in diameter. After that, everything spread out and cooled for about 330,000 years, when finally the fog cleared and the universe became visible. So that's how everything got going, which I think is a pretty fantastic story, and probably much stranger than anything our ancestors came up with by way of an explanation. But the next thing that happened, well, that's pretty spectacular too. This is the universe seen in extreme fast forward. All 14 billion years in less than a minute. It shows how the universe changed from a cloud of gas into a place filled with perhaps 100 billion galaxies swirling in a vast, chaotic dance. What I love to get people thinking about is that all this had to be built atom by atom. Celestial engineering on a spectacular scale. So what drove this cosmic clockwork? I'd say it was the force of gravity. The idea of gravity was worked out by Sir Isaac Newton, who had the same job as me
here at Cambridge University back in the 17th century. It supposedly dawned on him when an apple fell on his head. The apple helped him realize that all objects attract each other. And the greater the mass, the stronger the pull. These apples are attracted to the Earth, and although you can't see it, the Earth moves very slightly up towards the apples. All things come together through the power of gravity. Gravity was created in the Big Bang, and has been at work ever since. It's what keeps you, me, and apples stuck to the Earth. In the early universe, gravity had a much bigger role to play.
Right after the Big Bang, the universe was just gas, almost perfectly spread out throughout space. Over the next 200 million years, gravity began to pull the gas back together to produce the very first structures from which everything else would grow. But even this very nearly didn't happen. If it weren't for another stroke of cosmic luck, there would be no you, no me, no stars or planets or anything at all. We know this because in 1982 a group of scientists, including myself, spent 3 solid weeks working it out. Although the calculations were hard, demonstrating what we discovered is easy. First, I need a nice flat floor, like this one, for example. This is the dining room in my college. I'm going to fill the place with lots and lots of ball bearings. These balls represent the matter of the early universe, a thin gas spread out evenly across the vast cosmos. Here's where luck comes in. If they're all the same distance apart, gravity pulls each ball the same amount in all directions. They stay perfectly aligned, and precisely nothing happens. Fortunately, one of the basic rules of the universe is that nothing's perfect. Perfection simply doesn't exist. The early universe had a tiny unevenness that can be simulated by removing just 5 ball bearings. It may not look like much has changed, but to gravity, those missing balls create a giant opportunity. Gravity now pulls more strongly on one side of some of the bearings. The tiny irregularities in the sea of ball bearings have given gravity something to sink its teeth into. And this is exactly what happened back where we left the young universe. Parts of the sea of early gas were ever so slightly thinner than others. The less dense areas were like the gaps between the ball bearings. The denser parts of the sea of gas where gravity was having its way, clumped together. And it was in these areas that all the stars and galaxies would form. The cosmos had taken its first step towards the beautiful place it is today. All thanks to irregularity, imperfection, a lack of order. So next time someone complains that you have made a mistake,
tell them that may be a good thing, because without imperfection, neither you nor I would exist.
$13.5 billion years ago, the universe was mostly hydrogen gas, with gravity doing what gravity does, which is to slowly pull it into vast clouds. Hydrogen is the simplest of gases, but it has a very special property. It's a tremendous source of power. Heat hydrogen to around 10 million degrees and it begins to produce the energy that makes the stars shine and supplies the universe with warmth and light. To see how this works, let's imagine we could make a small star here on Earth. First, we need plenty of hydrogen gas. About a sports stadium full would be perfect. Next, we need to imagine squishing this hydrogen together, just as gravity does in space. As the hydrogen compacts, the atoms of gas start bouncing off each other, and the temperature begins to rise. By the time it's compressed down to the size of a soccer ball, the hydrogen reaches the critical 10 million degrees, and a process called nuclear fusion begins. The hydrogen starts to fuse together, making a new, heavier material, helium. With every step of this tiny bump and grind, some matter gets converted into pure energy. We have created a miniature star. Of course, if this was a real experiment, you wouldn't want to go anywhere near it. The energy given off, even from a star this small, would be devastating. Back in the early universe, the same process happened for the first time on a much, much bigger scale. Gravity compressed the hydrogen gas clouds over millions of years until deep in the center, the hydrogen became hot enough for fusion to occur. The first star burst into life, pouring its energy into the vast universe, a product of the laws of nature and the raw materials left over from the Big Bang. It was almost 1,000 times bigger than our own sun and burnt a deep blue. What's more, this star soon had company. The stars were turning on. This same process still happens in our sun, which is where we get the energy we need to live. But there was still a long way to go to get from this to where we are today. You can't build a world like ours from simple gases, such as hydrogen and helium. You need all sorts of other elements. You need elements like oxygen and carbon and iron and many more. But we got lucky yet again, because the very same process that causes the stars to shine also just happens to make materials like oxygen and carbon and iron. Stars, simply by accident, are giant factories. To see a star in action, let's imagine I could split one in half. Just as in the soccer ball star, the hydrogen atoms are fusing together, creating helium, which produces the star's energy. But helium is slightly heavier than hydrogen, so it sinks to the center of the star. And now the helium atoms take center stage. As they fuse together, they produce even more energy and form yet another new element, carbon. A vital building block of every living thing. The process repeats itself over and over, and the star becomes layered like an onion. A really big onion. The closer to the center, the heavier the elements, like neon, oxygen, and last of all, iron. Now things change. Iron doesn't produce energy when it fuses, so the fire begins to go out. More and more iron builds up in the star's core until almost all the remaining fuel runs out. Now gravity takes over and squashes the star in on itself. As its core gets more and more compressed, its temperature soars until it's over 100 times hotter than the core of our own sun. Finally, the star collapses and explodes. This is a supernova. The death of a star and the birth of something new. In these brief microseconds, a massive shockwave passes through the star. The blast is so powerful that it forces some of the iron to fuse into even heavier elements. And that's how heavy elements, such as gold or platinum or lead, are made, forged in the heart of an exploding star. So if you have a gold ring, make sure you appreciate it. The metal was made in a blinding flash of light billions of years ago. The finale of the process that produced the elements all around us today. It never ceases to amaze me that our bodies are constructed of the stuff of stars,
and that our hearts beat because of the energy given off as those materials are made. But as magical as a star is, there are even more fascinating and powerful things in our enormous cosmos.
Around 300 million years after the Big Bang, the early stars began to form galaxies, which slowly took on a bewildering variety of shapes and sizes. Our galaxy, the Milky Way, is thought to be one of the oldest, having started to assemble itself some 13 billion years ago. It's roughly 6,000 billion miles in diameter and contains something like 200 billion individual stars. Nobody's quite sure exactly how many, since they can't all be seen from Earth, and anyway, it would take a long time to count them. Because all these stars were built by gravity, you could say gravity's the hero of the universe. After all, it turned a meaningless soup of gas into something of beauty and power. But like all interesting heroes, gravity has its dark side. Right in the center of our galaxy lies an example of what happens when gravity rules unchallenged. A black hole. When I was in my 20s, I did some of the basic
Mathematics of black holes, but few people shared my fascination. These days, they are a popular subject.
Physicists all over the world are studying black hole behavior. We now know that black holes are not only fascinating in their own right, but that they play a fundamental role in the formation of galaxies. They also give us a glimpse of how the universe may end. A black hole forms when a large star, one say 20 times the mass of our sun, comes to the end of its life. Such a star looks nothing like our sun because it's become unstable, convulsing violently as its death throes begin. Finally, it runs out of fuel and begins to shrink, getting denser and denser, hotter and hotter. But with a star this massive, there is no force in the universe capable of stopping the collapse. The core is so heavy that it just keeps on falling in on itself. Gravity is running wild. In just 15 seconds or so, the unstoppable force crushes the star from millions of miles in diameter to as little as 12 miles in diameter. All the mass that was in the star is still there, but its own weight keeps forcing it down smaller and smaller still. The temperature of the core soars to 100 billion degrees. The outer layers are blasted away in a massive supernova. But deep in the center, the core falls down what we call a gravitational well. It crushes itself into a single point. A black hole is born. Nothing nearby can escape its pull, not even light. It's hard to imagine just how dense a black hole can be. But I'll try and put it into perspective using something familiar. The Earth. Imagine, piece by piece, I could compress our planet and crush it until gravity took over and it became a black hole. how small would it have to be to vanish down its own gravitational well? From 8,000 miles in diameter, I'd have to crush it to the size of a pea. In my years studying black holes,
one of my most unexpected discoveries was that a black hole cannot be perfectly black.
for much the same reason as the early universe could not have been perfectly spread out. There is no such thing as perfection. Black holes must give off radiation. The smaller the black hole, the greater the radiation. An even tinier black hole with only the mass of a mountain range would actually shine. Out in space, most black holes are much larger. The smaller ones have around 4 times the mass of our Sun and are 15 miles in diameter. Some are much larger, containing the mass of thousands of suns. And then there are the really big ones. Supermassive black holes that exist at the centers of galaxies like our own. This black hole is thought to have the mass of 4 million suns and a diameter of 11 million miles. Black holes like these are the heavy hubs around which many galaxies, including the Milky Way, rotate. A kind of stabilizer that gives them form and shape. So 8 billion years after the Big Bang, after a long and remarkable run of good luck, we have stars and we have galaxies slowly rotating around giant black holes. Now the scene is set for something close to our hearts. The formation of our Sun, the Earth, and ultimately, us. Our solar system, the place we call home, lies about 26,000 light-years from the center of our galaxy, the Milky Way. Or around 2/3 the way out. The story of how these huge planets came to be orbiting an average yellow star is 6 billion years long. And since we don't have that much time, I'll speed it up a bit. It starts with a bang. Long ago, an ancient star exploded, littering space with swirling clouds of the materials it had made while it lived and the heavier metals it created as it died. We know this because we can see similar fields of dust out in space today. They are called nebulae, and they are very beautiful. Every nebula is different, and in our case, the clouds contained nitrogen and oxygen and iron and silica and all the other stuff needed to build a world like ours. Then the tireless force of gravity started to pull it all back together. And the heavy engineering that produces planets began. Vast spirals of dust began to form. And at the center of one of these, a rocky planet called Earth started to take shape. Built of stardust and assembled by gravity. Fast forward 100 million years, and it had grown into a giant ball, sweeping up billions of tons of celestial debris. This is where the Earth came from, and therefore how you and I began. But our planet would have remained a large, sterile ball of rock and metals and minerals forever, were it not for one more event, one more expression of the forces of nature. 93 million miles away, at the heart of the giant nebula, the pressure and temperature of a ball of hydrogen gas had become so great that the atoms were beginning to fuse. A new star, our sun, was coming to life. As the sun ignited, it gave off a huge blast of solar wind, a radioactive gust of energy. This blew all the remaining dust and gas that was left over from the nebula out to the edge of the solar system, which is why everything is nice and orderly today. In the outer reaches of the solar system, we have the huge gas planets, Jupiter, Saturn, Uranus, and Neptune. Further in are the denser, rockier planets, Mercury, Venus, Mars, and of course, the Earth. Lucky for us, the Sun is 865,000 miles in diameter, or just the right size to burn consistently for a very long time. 8 billion years. Long enough to allow the next development to take place. Life. Life is one of the strangest phenomena known. In my opinion, it shows that the universe is capable of almost anything. Yet it amazes me that we can know so much about how the universe began many billions of years ago. But we have yet to discover how life itself began. The most likely explanation is probably that we are an accident. Just by chance, some molecules bumped into each other at random until finally one formed that could copy itself. Then began the slow process of evolution that led to all the extraordinary diversity of life on Earth. Life seems to be simply what matter does, given the right conditions and enough time. I think that life is probably quite common throughout the universe, but that's another tale altogether. As life developed, it changed the planet on which it was born, altering the very fabric of the Earth. After 4.5 billion years, the human race arrived on the scene. But one thing often troubles
People when they hear this story. How could such an astounding chain of events, which resulted in us, be an accident? Perhaps science has revealed there is some higher authority at work, setting the laws of nature so that our universe, and we, can exist.
On the face of it, life does seem to be too unlikely to be just a coincidence. Think about it. The Earth lies at exactly the right distance from the Sun to allow liquid water to exist on its surface. And the Sun just happens to be the right size to burn for billions of years, long enough for life to have evolved. The solar system is littered with all the elements needed for life. these elements themselves are only possible because of older stars that have burnt out. These older stars only existed because of a tiny unevenness in the early primordial gas that was itself produced by a 1 in a billion imbalance in the sea of particles that came from the Big Bang. So is there a grand designer who lined up all this good fortune? In my opinion, not necessarily. Look at it this way. What if there were other universes, ones not as lucky as ours? Each of these universes could have come from its own Big Bang, with different laws of physics and different conditions. In some, gravity might not exist, and there could be no life. In others, hydrogen might not fuse, so there would be no stars, and again, no life. And for any number of reasons, universes could have come and gone without producing anything at all. So perhaps we should not be too surprised to find ourselves in a perfect universe, orbiting a perfect sun on a perfect planet, because such perfect places are the only ones where life like us can exist. We are one of the many products of the universe, the result of an ancient and elegant mechanism. But even this remarkable discovery is only just the beginning of what physics can tell us. We can find out what humankind will face in the distant future. And ultimately, we might discover the fate of the universe itself. One reason I love cosmology is that it tells us not only where the vast web of galaxies in our universe came from, but also what lies in store for both the universe and for us. I think it's pretty exciting to be among the first human beings able to look forward for hundreds and even billions of years, maybe as far as the end of time itself. What I see is not only the future of the cosmos we inhabit,
but also the enormous challenges our species will face. After all, we are puny organisms compared to the mighty universe that made us. Even the Earth that gave us life will not always be the blue sanctuary it is today.
The continents of our planet are drifting. Fast forward 75 million years, and they will be clustered towards the South Pole. No one knows if the Earth will still be habitable then, but the sad truth is that we may not last long enough to find out. As we gaze into the future, it turns out that the universe is a pretty dangerous place. Just look at our neighborhood. It's littered with billions of asteroids, ancient remnants left over from the process that built the solar system. The possibility of one of these wiping us out isn't just the stuff of Hollywood disaster movies. The threat from asteroids is real. We've even given some of them names. This one is called Apophis, after a mythical Egyptian demon, a god of darkness and destruction. Discovered in 2004, Apophis is the size of a 100-story skyscraper. It weighs about 20 million tons. Speeding through space at 28,000 miles an hour, 10 times as fast as a bullet, it carries almost as much energy as all the world's nuclear weapons combined. And we know roughly where it's headed. The precise path is not yet fully known. But on April the 13th, 2029, this huge rock is likely to pass within 23,000 miles of the planet's surface. Close enough to pass beneath satellites in orbit around the Earth and give us all the scare. Luckily, there's very little chance that Apophis will actually hit us. But the problem for humanity is that in space, there's always a bigger rock. There are thousands of really large asteroids out here. Some are over 10 miles long, the size of Manhattan. An asteroid this size hits the Earth every 100 million years or so. The last one struck the Earth 65 million years ago, and probably was responsible for wiping out the dinosaurs. We don't know when the next asteroid will strike, but if it was big enough, it could sterilize our planet. That would be the end of the 5 billion year long story of life on Earth. But even if we avoid such a natural catastrophe, we could all too easily end up destroying ourselves. In the last 10,000 years, humans have come to dominate the planet. We're so successful that it's tempting to think we are evolution's grand prize. But I believe intelligence is probably overrated. It's not necessarily a good thing for a species' survival. Bacteria have managed without it for over 3 billion years. Intelligence, at least in our case, leads to technology. And there are many ways technology could wipe us out. The most obvious, of course, the threat from nuclear weapons. Even if the risk of a nuclear war happening in 1 year is minuscule, say only 1 in a million, if we run those odds over 100,000 years, the chance of catastrophe falls to 1 in 10. Personally, I worry that even this might be over-optimistic. Although we are clever enough to have designed such weapons, I'm not sure we are clever enough not to use them. As time marches relentlessly into the future, the universe has other surprises in store. There are some powerful things out there, some of which could destroy the Earth without any help from us. As the universe continues to dance to its ancient rhythm, stars will come and go in a relentless cycle. And because there are hundreds of billions of stars, there's always one dying in a supernova somewhere. In our galaxy, for instance, a star dies every 50 years or so, which is but the briefest of moments to the universe. It's just about conceivable that a supernova could damage the Earth, if you consider the likelihood over a long enough timescale. One kind of supernova, discovered entirely by accident, is thought to be particularly dangerous. In 1967, when the Cold War was at its height, US military satellites picked up a massive burst of something called gamma radiation. Gamma radiation is the most dangerous type of radiation known. It's also the telltale sign of an atomic weapon. Were the gamma rays detected evidence of a new and powerful Soviet bomb? Thankfully, the answer was no. After careful analysis of the data, they discovered that the sudden bursts of gamma rays were actually coming from space. Not even the Russians had that kind of technology. Decades later, we still don't have proof of what causes the bursts of radiation. But there's a well-respected theory that they are produced by a special kind of supernova called a gamma ray burster. What's more, there might be one quite nearby. Hidden within this massive spiral plume of plasma, 8,000 light-years from Earth, is a star called WR104. Deep inside the star itself is a bright sphere, throwing off a shell of hot gas as it nears its end. If this star is what we think it is, then as it dies, it will produce two tightly focused beams of radiation, one from each pole. The star destroys itself as it produces these beams, which contain more energy than our sun will produce in its entire life. The brightest known phenomena in the entire universe. No one is sure if WR104 will do this, or if the beam would strike the Earth. But if so, we could be bathed in high-intensity radiation, with some devastating consequences. The beam would cause spectacular auroras, stripping the ozone from the atmosphere, allowing deadly radiation from the sun to strike the Earth. It may sound like science fiction, but this could be the second time skies like these have been seen on our world. 450 million years ago, over half of all living creatures were wiped out in a great extinction. One explanation is that a gamma-ray burster irradiated the planet so badly that Earth's ecosystem virtually collapsed. I don't want to worry anyone, but I think it's definitely a good idea for the human race to venture far beyond the Earth. We would be wise to keep our eggs in as many baskets as possible.
Thankfully, that process has already begun.
In my opinion, the launch of Apollo 11 is probably the most important moment in human history. It was a turning point for the universe too. Life, in the form of us, escaped its home planet and stepped on another surface. The astronauts' footprints stand preserved to this day. A testament to the beginning of what I think could be the next chapter in the story of the cosmos. The spread of life to other parts of the universe. As the universe gets older, we will have to get wiser. I think we'll have to go much further than the moon. At the very least, to Mars. The red planet is likely to play an important part in our evolution, and maybe even in the story of the cosmos. It's the second and possibly the most important stepping stone on humanity's journey to the stars. Robot missions to Mars have revealed a spectacularly beautiful, yet dangerous and desolate place. I imagine that being a human pioneer here would be an exciting business. For a start, it's cold. It's 50 million miles further from the sun than the Earth, and so it receives half as much warmth, and the temperatures fluctuate wildly. From 80 degrees to minus 200 in a matter of minutes. If the cold doesn't get you, the low gravity will. Mars is just half the size of the Earth and has just 38% of its gravity. Over time, explorers' bones would weaken and their muscles would waste away. Spend long enough on Mars, and you could find yourself too weak to safely return to Earth. The low gravity also means Mars struggles to hold on to an atmosphere. Here, there's nothing more than a thin wisp of carbon dioxide at just 1/100th the pressure of our air. Mars is also bathed in harmful radiation from the sun. Even though it's further away, unlike Earth, it has no magnetic field and no ozone layer to protect it. Early explorers would have to be careful to minimize their exposure. Perhaps they'd even have to live underground. But one day, I think it'll be possible to drastically alter conditions on Mars, perhaps using space-borne mirrors to supply warmth and power. With perfectly foreseeable technology, much more could become possible. If we could erect giant domes made of glass and plastic to block out the radiation, inside them we could enrich the atmosphere. 500 years from now, which really is a very short time indeed, I think Mars will have its own language, its own currency, its own cuisine. Although I'll bet you'll still be able to get a hamburger somewhere. But it's clear that as the universe continues to age, even advances like these will not be enough to guarantee humanity's existence for a very long time. Look further into the future, and ultimately our solar system will follow the same path as countless billions of solar systems before it, and cease to exist. Right now, the Sun is in the middle of its life cycle. During this phase, it is getting gradually hotter and brighter all the time by about 6% every billion years. In about 5 billion years, the Sun's temperature will have grown to nearly 200 billion degrees. At this point, the Earth will be an unrecognizable ball of molten rock, all life having long since perished. This is our planet's unavoidable destiny. But that's not all the Sun has in store. As it runs out of fuel, the Sun will start to expand, turning into what's called a red giant. It will change from being the object that gave us life to the one that annihilates it. In about 7 billion years, the Sun will be 200 times bigger, about 200 million miles across. So vast, it will obliterate the inner planets one after the other. Mercury, Venus, and most probably the lifeless Earth. But as the universe continues to evolve
at its own relentless pace, new opportunities will present themselves to us if we are able to preserve the life that the cosmos made.
This is Gliese 581d. It's a large, rocky, Earth-like planet, the nearest known. It's just possible that this world, or one like it, could in the future become home to the human race, a second sanctuary against the unforgiving blackness of space. Discovered in 2007, it's 7 times bigger than Earth. It orbits a star smaller and redder than our own, but it lies at just the right distance from its sun to allow water to exist on the surface. But even if this is the perfect home away from home, there is a fundamental problem we will have to overcome. Gliese is a very, very long way away. More than 20 light years from Earth. That's 120 trillion miles. To get some idea of this extraordinary distance and the challenge it presents, I'm going to imagine that we could hitch a ride on the fastest man-made object in existence. Voyager 1 was launched in 1977. Now over 30 years old, it's traveled more than 13 billion miles. Its mission so far has taken it to Jupiter and Saturn. By using their gravity to boost its speed, the little spacecraft has entered the record books. It might not look fast, but Voyager is racing through space at 11 miles a second. On Earth, 11 miles a second looks like this. It's 39,000 miles an hour. At this speed, we could circle the globe 1.5 times in an hour. So how long would it take a spaceship traveling at Voyager's speed to get to the nearest Earth-like planet, Gliese? The answer reveals the true scale of the cosmos. For even traveling at 11 miles a second, the journey to Gliese would still take over 350,000 years. I think we have a chance to become a lasting part of the ever-changing universe and to discover what other wonders it might hold. But to do this, we will have to develop new technology on an enormous scale. And that's going to take some serious engineering.
There are many in the field of cosmology who believe, as I do, that finding ways to travel great distances will be essential to keeping humankind alive in an aging universe.
If we could build a machine capable of traveling to other solar systems, we'd open up a fascinating possibility: the survival of the human race for billions of years. Present-day engineers have begun thinking about the principles of building such a ship. This is what it might look like. It could use atomic energy, or perhaps more exotic fuels such as antimatter, supplying it with enormous amounts of power. Yet I think the main challenges won't be technical. The first will be financial. The cost of constructing an interstellar spacecraft would be huge, and for the society that made it, there would be little payback. They would never see it again. So constructing such a machine will either be the greatest act of generosity in history, or it will have to be funded by the travelers themselves. And that raises the second problem. Even if it could travel mind-numbingly fast, say 1,000 times faster than Voyager, 11,000 miles a second, a journey to the nearest star system would still take 73 years. Such a long trip means that at least one whole generation of humans would have to live their entire lives in space. And we couldn't exactly say they had volunteered for the mission. The ethics of sending a human cargo on such a voyage would have to be carefully considered. Unless we could extend human lifespans to long enough to make such massive journeys. That, I think, is what we will ultimately end up doing. The process has already begun, as I know from personal experience.
My muscles no longer function, although my eyes and my brain are still working pretty well. But technology helps me to move and communicate. In the future, technology will do much more than that for all of us.
Within the next 1,000 years, we will see unprecedented changes in our physical capabilities. Genetic engineering will give us longer lifespans and greater intelligence. Modifying our genes could give us skin that protects us from radiation, the ability to breathe poisonous atmospheres, resistance to infection, we may even develop sophisticated artificial life forms using synthetic DNA, custom designed for the challenges of space travel. These advances would allow us to survive long journeys and inhospitable worlds. I imagine a time when our descendants spread to planets orbiting other stars all over our galaxy. And perhaps further still, carrying their biological cargo to solar systems we have yet to discover. Ships like this one could be designed to split up and spread out. A true diaspora of life that would have started with us. As we journey across interstellar space, I'm sure that we will unlock nature's deepest secrets. My great hope is that we will discover how the universe will end and solve the ultimate mystery: why the universe ever existed at all. I once gave a lecture in Japan where I was asked not to mention the end of the universe in case it affected the Japanese stock market. Well, I don't know if
or when the universe will end. But for those of you who are nervous about your investments, I think it's a bit early to sell.
At 13.7 billion years old, our universe is still in its youth. The earliest date we cosmologists think it could end is 30 billion years from now. There's still plenty of action to come. Even long after our sun has died, new stars will be born, some of which will have new planets around them, made of the same atoms that make you and me. Maybe we'll end up as part of some future alien ecosystem, although that's probably a bit of a long shot. What's true is that we are only the temporary custodians of the particles which we are made of. They will go on to lead a future existence in the enormous universe that made them. Certainly Certainly, gravity will continue its tireless, incessant work. It will go on shaping the vast strings of galaxies as it has ever since the Big Bang. Using supercomputers, we can simulate how gravity, even now, causes galaxies to be attracted to one another, resulting in vast, slow collisions. Our galaxy will merge with its nearest neighbor, the Andromeda Galaxy, in around 3 billion years. A slow-motion collision that will take place over 2 billion years. The same process is happening all over the cosmos. Entire clusters of galaxies are constantly colliding and reforming. Giant collisions as trillions of stars pull on one another, their vast masses causing them to spin and dance. Gravity is driving the cosmic clockwork as it has done ever since the Big Bang. This is what the universe looks like when we are released from time on a human scale. But will this cosmic whirlpool go on forever? As an endless maelstrom of mass and energy, space and time?